All right, this was the problem that you started in recitation and that you're finishing up here. Um, in your recitation, I asked you to draw three pictures of three different moments in this problem. I'm going to motivate why you need three by first only drawing two and then talking about how that's not enough to figure out what's going on. So in the first picture, I'm going to Ohana is the person and Room is the dog. So this problem is based on a real person and her real dog. This was Room the physics dog, who has been in a lot of our problems because he's so cute. So we started with, we'll make Ohana red. I believe that's her favorite color. So Ohana is here. Room is running toward her at some speed v naught. And then in the final picture, Room has jumped on top of her, like he likes to do. And both of them are together. Oops, wrong tool. Erase that. I'm still learning to use my stylus. I will get better at this. Again, all of your faculty are learning right aside you with this whole online class thing. We are being as patient as we can with everything. Um, you all have been fantastic to work with. We have to beg your patience a little bit too. So this swing angle is theta, and at this point they are not moving. I'm going to call this V2, 0. So in this unit, we're studying conservation of energy and conservation of momentum. So let's ask, can we use any of these techniques to get from picture 1 to picture 2? It turns out no. Energy is not conserved, or at least mechanical energy is not conserved, because this collision between Room and Ohana is an inelastic collision. When he jumps in her lap, they stick together, they don't bounce off. Kinetic energy is lost in that collision. So kinetic energy is not conserved, and worse, we have no way of understanding exactly the forces involved in that collision. We don't know how long it takes, we don't know how big the forces are, so we cannot use the work energy theorem to understand the collision. But we also can't use um, conservation of momentum, because as the swing starts to swing upward, there's an external force, right? There's an external force from the tension in the rope, pulling the two of them attached to the swing up and to the left. The trick is to understand that this problem is really made of two motions, two different things happening, separated by an intermediate picture. The intermediate picture is right after the collision. And at that point, after the collision, the two of them have not yet started to swing upward, but they're moving to the right at some speed v1. So we've discussed that we can use conservation of momentum to understand what happens in the collision, because a collision is just a split second of an instant, and in that instant, momentum I can spell. Actually, I can't late at night. In that instant, external forces are very small compared to the force in the collision. But now as Room and Ohana start to swing up into the air, we can use the work energy theorem because during that motion, I can keep track of the work being done by all forces. One of the things that will be important for me to label on my diagram, I already know it, so I'm just already going to draw it, is remember that when you're calculating the work done by a force, all you care about is the displacement in the direction of that force. So I need to know the vertical displacement here. I'm going to go ahead and find it because I know I will need it to calculate the work done by gravity. This just saves me a little bit of time and space in drawing my diagrams. There's a trick to finding this. So we know the total length is L, which means I also know that if I think about this right triangle here that I'm drawing in magenta, that this length is L cosine theta. But since the total length is L, that means that this little piece down here is L minus, L cosine theta. So the vertical displacement then is L minus L cosine theta. That will be important when I calculate the work done by gravity. I should note that this is the most important problem in this homework set for you to understand. If you understand this single problem right here, that is the single most important thing you can do in preparing for exam 3. This problem is a complete classic. It's on every homework assignment whenever any professor in the entire country teaches this problem. Often it's a bullet being shot into a block of clay, but we prefer cats and dogs rather than bullets in this class. So now that I have my approach in mind, let's do it. So I'm going to use conservation of momentum to relate V0 to V1. So the initial momentum, whoops, I'm on the wrong tool again. I keep forgetting to switch off of my line drawing tool. So I know that the initial momentum, actually I'm going to write it this way. I'm going to label my pictures. Picture A, picture B, and picture C. This will help keep things straight. So I know that the momentum in A equals the momentum in B. Now in picture A, only room has momentum. I know that looking at the problem, Room, the dog, has half of Ohana's mass. So we're going to call Room's mass M, and we're going to call Ohana's mass 2m, because Room has got half of her mass. So for the momentum at A, that's going to be mv0, and the momentum at B is going to be mv1 plus 2mv1, Room plus Ohana. They're both moving at the same speed because he has jumped in her lap. So this pretty obviously gives us that V1 is equal to 1/3, V0. Yep, that's right. So the conservation of momentum part was pretty easy. We have done that. So this, again, lets us understand the relationship between A and B, and thus how V0 relates to V1. Now for the work energy theorem part. I know that, draw draw a dotted line here. So I'm going to say that the kinetic energy at position B plus the work done in going from B to C equals the kinetic energy at C. You could also do this problem with potential energy, but my experience is that students need more practice on understanding what the work energy theorem means. They're exactly equivalent. You can do this with potential energy. You will get exactly the same answer, but this approach I find to be in a way more direct and also more educational for students. So that's why I'm choosing it to do this way. Choosing to do it this way. I need a nap. So the kinetic energy at B is 1/2. Oh, no. Sorry. There are two objects together, right? The total mass here is 3m. So I've got 1/2 times 3m v1 squared plus the work done by gravity. So the work done by gravity is going to be F-grav times the displacement parallel to gravity. And the kinetic energy at C, 1/2, again, forgot my factor of 3, because 3m times v2 squared, but v2 is 0, so that whole term goes away. Now, here is where we use the thing we did before. Remember, we figured out, I'm going to draw this in yellow so it doesn't get in the way. Depending on your screen, you may have to look carefully, that the displacement parallel to the motion, the displacement parallel to the force of gravity, the one that counts for work, is L minus L cosine theta. And the force of gravity, again, is just going to be 3mg. The displacement parallel to the motion is L minus L cosine theta. So now I can substitute all of that in. One more thing that I can cancel. I'm going to write one more line of algebra before I cancel that. Kind of debating what order to do these steps in. So this gets me that 1/2 times 3m v1 squared plus 3mg times L minus L cosine theta equals 0. I can cancel the 3m's. And this tells me that v1 squared, well, v1, I'll just do it all in one bite, is the square root of 2L minus L cosine theta. So we have now related the other piece of the problem. We've related piece B to C to figure out what V1 is. Now we go back to this part, the thing we did just a moment ago, where we found that V1 was 1/3 of V0. Excuse me. So if V1 is 1/3 of V0, then V0 is 3V1, which is just going to be 3 times the square root of 2L minus L cosine theta. So that's this problem. Notice that I almost ran out of room, right? When I'm doing these problems, I have to plan out how I'm using my paper. And notice that I used a full half of the page to plan what techniques I'm going to use to understand different sorts of the motion. That's not an anomaly. That is a good approach to these problems. Um, it's kind of like measure twice and cut once, as you know, everybody's dad said to them, right? Um, in these problems, especially ones where you have to combine conservation of momentum with something else, it's always a good idea to draw clear pictures of different instants in the motion and plan out what techniques you're going to use to understand how you get from one picture to the next. Uh, I'll emphasize again, this is a very important problem to understand, so I would encourage you to go back and review this and ask us if you have any questions. Thank you.